GCSE Chemist. This is Dr. Beck with another chemistry video in the AQA syllabus. This time we are looking at the properties of hydrocarbon polymers and how they are different and how they are similar. So make sure you have all your equipment ready, make sure your phone is away and not going to cause you any distractions, and let's begin. The first thing I'd like you to do is a simple do now task. So you may need your periodic table. Ideally, you can do this without your periodic table. So I'd like you now to answer all of these questions about this element. This is the symbol you would see in your periodic table. You would also have a name. By now you should know the name of this element, but what I'd like you to do when I finish this sentence is simply pause the video. Try to complete as many of these tasks and questions as you can, answering them full sentences where you need to, drawing neat copies of diagrams and finish them off to the best of your ability. So please now pause the video, and when you've done, come back to it. Okay, hopefully you didn't find that too difficult. It's something which needs a bit of practice, but let's see how we have got on. Hopefully you know or you found that this element is carbon. So if you've got the word carbon, written the word carbon, give yourself a tick. How many protons? Well, this bottom number is what we call the atomic number or the proton number. So the number of protons is 6. How many neutrons? The top number is the total of the protons and the neutrons. Those are the particles with mass. So there are 12 things in the nucleus. 6 of them are neutrons, 6 of them are protons. The remaining 6 must be neutrons. How many electrons? Well, we've already established that the lower number is the number of positive protons. We also know that every atom is electrically neutral, therefore this is also the number of electrons. So electrons, 6. How many shells? Now this links also to the next question, but how many shells? Well, the first shell can hold only 2. It's got a 6 in total, so 2 in the first shell and 4 in the second shell. So this will have 2 shells of electrons with 4 in its outer shell. Now for the next 2 questions, you may have looked it up, but ideally we can work this out just from the data we have. Which group is it in? Well, we say that for the first 20 elements, the group number is the same as the number of electrons in the outer shell. So in this case, this will be in group 4. It has 4 electrons in its outer shell. Not in total, just in the outer or the final shell. Which period of the periodic table is this in? Well, again, you may have used the periodic table, but we can work it out from the information we have. This has got 2 shells of electrons. So we say that this is in period 2. The first period has only got 2 elements in it. The second period has more, but this is part of that second period. So just pause the video, check your answers, purple pen when necessary, and we'll move on to the next 2 questions. Okay, first part of the extension work was copy the diagram on the left and use it to draw the electronic structure of the atom. The atom was carbon. Now often we see atoms like this drawn with the element symbol inside. You don't need to, but it's useful. Hopefully you had something like this. 2 electrons in the first shell and 4 in the outer shell or the second shell. Those electrons can technically be anywhere in our GCSE diagrams, but usually we see the first shell, top and bottom, and the second shell. Often we see them in pairs. You don't have to. Here I've just drawn them all around the second shell. Second extension. The symbol for hydrogen is shown on the right. Use it to draw the electronic structure of hydrogen. Well, hopefully you didn't find this too difficult. We use the same rules as we did with carbon. We draw a circle. We can add the letter H to it, and we then need to look at our data. This lower number is the number of positive protons. So this means that an atom of hydrogen must only have one electron, and we can put that one electron anywhere we like in that first and only shell. So a very simple diagram like this. So again, give yourself a massive tick and a big pat on the back if you got those right, and we'll move on. Okay, today then we are going to look at the properties of hydrocarbon polymers. We're going to learn about hydrocarbon molecules so that we can describe how they form and explain their properties. We have lots of keywords for today, and we're going to use many of them, if not all of them. So I'd like you to, when I finish this sentence, please just pause the video and write down the information in your book so we can learn remotely. Okay, welcome back. So let's get on with our look today at properties of hydrocarbon polymers. First of all, what do we mean by hydrocarbon? Hydrocarbon and hydrocarbons, as it says here, are molecules that contain only carbon and hydrogen atoms. They are formed by covalent bonding between atoms. So how does that work? We're going to have only carbon and hydrogen atoms, and they're going to have covalent bonds. So let's have a look at the simplest hydrocarbon molecule first of all. And this one is called methane. Now this is quite a challenge, but I'd like you to copy this diagram and try to use the clues from the previous slides. If you need to go back, I'll just play the video and we can go back. I'll ask you to draw a dot cross diagram for a molecule of methane. Let's just go back to what it is. Hydrocarbons, only carbon and hydrogen. They are formed by covalent bonding between atoms. Let's have a look at this. So covalent bonding. I'd like you, if you can, to stop the video now and have a go without any further clues of how to draw a molecule, a covalent molecule of methane. So pause the video and have a go. Right, welcome back. Hopefully you've had a go at that in your book. If not, if you found that too difficult, here are some further clues. Okay, remember, hydrogen has got one electron per atom, and carbon has 6 electrons per atom, with 4 on the outer shell. Okay, so if you didn't quite get that right, if you didn't quite understand what you were doing, there's extra information here. So have another go and please pause the video. Right, hopefully you found that extra information useful because that is critical. Usually in these diagrams we only show the outer shell electrons. So I'm going to show you in a second the complete diagram. Here we go. Let's say that the dots are the carbon electrons. So we've got one here, 2, 3, 4 in total in the outer shell. We don't show the inner shell. And each hydrogen has just one electron. Now we're saying that the electron is this X for hydrogen, and each atom has now a full outer shell. This is now a stable molecule of methane. That's the simplest hydrocarbon. Let's have a go now at a more complex hydrocarbon. However, let's think about what that means for methane. Here are some methane molecules. Methane is a gas at room temperature. Each individual molecule is a covalent molecule held together by strong covalent bonds. However, between the molecules, there are very weak interactive forces, very weak forces between them. All of the bonding, all of the energy is contained within the molecule of methane. And there are very few interactions. And as a result, usually at room temperature, These things have enough energy to overcome these forces and separate from each other. So we then see methane is a gas at room temperature. There is enough energy to overcome any attractive forces, and these things at room temperature will be separated. Therefore, they will behave and will be a gas. Let's have a look at other gases. So here's a mix of many gases, and this is a typical view of the molecules we see in the air around us. Methane mixes with other gases. Now hopefully you can have a look. If you want to pause the video, you may. Try and identify some of these. We've got oxygen over here. We've got nitrogen, also a gas at room temperature. We've got carbon dioxide. We've got methane here, NH3. We've got argon atoms over here. And of course, we have our methane molecule. All of these are separate. All of these have very weak forces of attraction between the molecules. Therefore, at room temperature, these molecules and these substances will be gases. Okay, that's methane. Let's have a look at another hydrocarbon. Hydrocarbons are all related, and they all contain just carbon and hydrogen. So here we have methane, CH4. The next one is ethane, C2H6. How are we going to draw this molecule? Well, first of all, let's start with the two large carbon atoms. We're going to add those symbols, the two C's, to the central. And notice they're overlapping. These two are going to share a pair of electrons. To help me, I'm going to also add 6 more circles. And these will be the hydrogens. Remember, this is another hydrocarbon and another covalent molecule. So now we can begin to think. Each carbon atom has 4 electrons in the outer shell. So I'm going to draw crosses for those, including one in the overlap with the other carbon. Each hydrogen has got 1. I'm going to draw those 3 with their dot. Right, this other carbon is going to do something very similar. Now I'm going to draw those electrons for the second carbon atom like this, and hopefully you'll see why in a second. And then these hydrogens electrons are going to draw as these dots. Right, what do we have? We have C2H6. Every single atom there has a full outer shell. This carbon on the left has got 8 electrons in its outer shell, and it's sharing a pair with each hydrogen, and it's also sharing a pair with the adjacent carbon atom. And we're showing the 2 electrons. I've shown one with a cross and one with a cross with a circle, just to distinguish them. And the same thing with the other carbon, the one on the right. We have C with its 4 electrons, the crosses with the circles, and then we have the dots from the hydrogens and the crosses. So you can see that everything here has got full outer shell. It's really important as well to realize that the dots and the crosses and the other symbols, they're just electrons. They're all the same, but we've just shown the different symbols to help us to draw this nice and clearly. This is typical of the diagram you might see in a higher AQA chemistry paper. So this is usually the kind of level that we go to for GCSE. So here is one picture of a methane molecule. Who remembers the formula for methane? Shout it out of the screen now. Good. Hopefully you said CH4. CH4, methane. Now, there's another way. Instead of drawing all this out, we can show it like this, what's called a displayed formula. We have the central carbon, and then we have the 4 bonds around it. And these are shown with a single straight line. And this represents these electrons. We don't usually draw them, but if we can imagine, these are here. Now, to a chemist, then they just say, well, that's a covalent bond, a single covalent bond, a shared pair of electrons. That's the way we do it. So this one is our second molecule. This was ethane. So my challenge for you guys, first of all, is write down the structural formula. It's very similar to one we have on the left, CH4, but it is significantly different. And then have a go at displaying the structural formula for this second molecule, ethane. Stop the video, have a go. Okay, welcome back. So if you said C2H6 for ethane, give yourself a pat on the back. And here is the displayed formula for that molecule, for ethane. Again, if you did that right, give yourself a pat on the back, and we'll move on. A bit more difficult now. Have a go at these. These are the next two. Right, this one is propane. This one below is butane. So this is a little bit more tricky. So have a go at these two molecules of hydrocarbons in your book. Pause the video and come back to it when you're ready. Okay, let's have a look. So this one is C3H8, and you can see the covalent bonding, the sharing of electrons between the atoms. Here's the first one, and here's the second one. Give yourself a tick if you got those two. Well, here's a past paper question. Here's a past paper, genuine past paper exam question. I'm going to give you some time to do this by yourself. In the exam paper, it said, crude oil is a mixture of hydrocarbons. Complete the structural formula for the hydrocarbon that has 6 carbon atoms in its molecules. And in the exam, you were given a start. This isn't complete. You have to complete this structural formula, and you have to follow the clues that there are on the screen. So when you're ready, pause the video and have a go at this in your book. Right, great. So here's the mark scheme. Complete diagram with 2 carbon atoms and 5 hydrogen atoms, each C bond C and each C bond H linked by a single line or a bond. That's quite a complex mark scheme. Here's what it should look like. So this is the bit you were given, and this is the bit on the right that you should have been drawing. 2 carbon atoms, 5 hydrogen atoms, and a single line to represent a single covalent bond between each of those atoms. Again, if you got that right, 1 mark in an exam. Simple, move on. Dead easy. Okay, so today we've been looking at hydrocarbon and hydrocarbon polymers. Here's where we get into polymers. What does polymer mean? Polymers are very long molecules. They're atoms which are held together by covalent bonds. Between the polymer molecules, there are intermolecular forces. Now, so far we've seen fairly small molecules. Now we're going to look at much longer molecules. We've seen already methane and ethane and propane and butane. And those, hopefully you saw, were getting bigger and bigger as we were going down. The strength of the intermolecular force, this is the force between molecules, that increases with the size of the molecule. And I'll show you a model of this in a second. So what happens is hydrocarbon polymers have higher melting and boiling points than simple molecular substances like methane and like all those other gases I showed you earlier. This means they are normally solids at room temperature. Okay, let's unpack this a little bit. That's a statement. Let's have a look at why. On the left-hand side, we have methane. This is a slightly different way of showing the structure, but hopefully you can see it is still CH4. Now, the boiling point of methane is very, very low. It boils at minus 164 degrees Celsius. And there are very weak intermolecular forces shown by these red dots. If we have a slightly longer hydrocarbon chain, such as the one we looked at earlier, butane, well, the boiling point of butane is round about 0 degrees C. So the boiling point is at 0 degrees Celsius. So this will boil at 0 degrees Celsius. So this is much higher boiling point than methane. But look, here we can get an idea as to why. There are more intermolecular forces holding these molecules together. This is going to take more energy to separate these longer molecules. Let's have a look at the next one. We've come across this one in our past paper. This is C6 hydrocarbon, C6H14. This has a boiling point of 68 degrees Celsius, so higher still. And again, we've got a clue as to why. These red dots, these molecules are longer, they are bigger. There are more intermolecular forces, there are higher forces overall between these two molecules. Remember, in a gas there will be billions of these molecules, so lots of intermolecular forces. So this is a higher boiling point. And here, the highest one for this series is octane, boiling point above the boiling point of water. Okay, so when water is liquid, this will be liquid as well. However, when water turns to a gas, it evaporates at about 100 degrees Celsius. This will still be a liquid, and it will boil at a higher temperature. But let's have a look why. Hopefully you can see more intermolecular forces, more interactions between these. These are going to get tangled up. It's going to be more difficult to separate these. They're going to need more energy, so a higher temperature, to turn to a gas. The boiling point will be higher, and also the freezing point, the melting point, will be higher. That's the picture I've shown you before. Let's just unpack that a little bit. It's important to remember each polymer molecule, repeating units over and over again, is made of a strong covalent bonds within the molecule. However, between the molecules, there are these intermolecular forces. Inter means between. Intermolecular forces are very weak between those chains. This is a little bit like Velcro. One hook and eye of a Velcro, that's not going to be difficult to break at all. You're going to easily be able to undo that Velcro. If we have lots and lots of molecular forces, if we have lots and lots of Velcro hooks and eyes, then it's going to be much more difficult to separate. You need much more energy. This is a model that I like to show the series of hydrocarbon polymers. One of very few interactions, it's going to be easy to pull apart. Lots and lots, dozens, hundreds, going to be much more difficult to pull apart. And this is what happens with the chemistry of these polymer molecules. Okay, to finish off then, a review of what we've been looking at today. Question 1, polyethylene is a long polymer molecule made of carbon and hydrogen only. Methane is also made of carbon and hydrogen only. Why does polyethylene have a much higher melting point than methane? Question 2, ammonia is a simple molecular substance. Explain why it has a low melting and boiling point. And also, a bit more challenging questions here. Explain why methane cannot conduct electricity, and also hydrocarbon polymers do not conduct electricity. Why not? Quite a challenge there for some of those, so have a go in your book, those questions. Stop the video when you're ready and come back to me when you're finished. Okay, welcome back. Polyethylene is a long polymer molecule made of carbon and hydrogen only. Methane is also made of those two elements, but polyethylene has a much higher melting point. Well, I could sketch polyethylene, lots and lots of carbons. These are all the carbons, and they're surrounded by the hydrogens. There will be another polyethane molecule near it. These are very, very long molecules. Okay. There are going to be lots and lots of intermolecular forces. Polyethylene has more intermolecular forces and more energy is needed to overcome them. Okay, the converse is that methane has much weaker intermolecular forces. Okay, give yourself a tick if you wrote something like that. That is our explanation. Question 2. Ammonia is a simple molecular substance. Explain why it has a low melting and boiling point. Well, you may have seen in the picture earlier, we have ammonia, NH3, something like this. Apologies for the circles. There are very weak intermolecular forces between ammonia molecules and these forces are overcome at low temperatures. Because not much energy is needed. These intermolecular forces can be overcome easily with very little energy, and that means at low temperatures they will have they will melt and they will boil, very low temperatures. Methane cannot conduct electricity. Well, it can't. Why? Electricity is the movement of charge. If you remember, these are covalent molecules. Methane has no free electrons or free ions. So the charges do not move. Okay. Again, this is true for all hydrocarbon polymers. So the key word here is covalent bonds. No free ions or electrons. So charge cannot move. And normally we say cannot move through the material. Okay, through the material. Okay. You may have used another word. You may have used the word delocalized. If you did, fantastic. Delocalized electrons. There are no delocalized electrons to carry that charge. Good, well done. Okay, so today then we've been looking at hydrocarbon polymers, what they are, how they're formed, how we can draw them, and we've looked at the intermolecular forces between them so that we can explain their properties. And we've seen all kinds of ideas, and hopefully now we have a better understanding. To summarize then, let's have a go at this challenge. This again is from a past paper question. Look at the graph below. Loads of information there. Describe the patterns seen for the melting and boiling points. Explain these patterns using your knowledge of structure, bonding, and forces. Wow, there's a lot there, guys. So, when you're ready, stop the video and then come back to me when you are finished. Okay, welcome back. If you're stuck with this, here is a sentence starter. So this might give you an extra clue. So if you really are stuck, pause the video again and use this to help you with your answer. Okay, if you really are still stuck or want extra help with the second question, here are some more clues and some keywords. If you manage to do it without any of these keywords, and in fact have used them without my hint, well done. These are words which are going to be really important. When you're ready, let's move on to the next part. Okay, so our trend. Well, we tend to use the labels. Let's do ourselves a favor. As the number of carbon atoms in the chain, and we're talking about the length of the polymer molecule. As that increases, the melting point and boiling point increase. So one thing, if you set something like this, in longer chains, there are more intermolecular forces. So more energy and higher temperature are needed to overcome them. Okay. As the number of carbon atoms in the chain increases, the melting point and boiling point increase. In longer chains, there are more intermolecular forces, so more energy and higher temperature are needed to overcome them. And that's it for today. Excellent. Hopefully you've enjoyed that. Leave me a comment if you have. Today we've been looking at the properties of hydrocarbon polymers. Thank you for watching.